Welcome to another IoT Central MicroSession. Please send any questions that you might have in the chat, and we will follow up with any unanswered questions using the email address that you registered with. My name is Jenny Plunkett, and I'm a Senior Developer Relations Engineer at Edge Impulse. In today's video, I will show you how you can easily create an Edge machine learning classifier to detect anomalous sensor readings using only nominal training data for embedded machine learning models directly in the Edge Impulse Studio. Edge Impulse is the world's leading embedded machine learning platform. It helps you build a full end-to-end machine learning pipeline to accomplish a variety of ML tasks from regression to vibration and sound classification to object detection and even predictive maintenance. You can import data from almost any source, including any sensor, and deploy your model to almost any device. You can maintain control of all of your data and firmware throughout the entire pipeline. The Edge Impulse Studio is an online platform that handles everything, including collecting your data from your embedded sensors, labeling the data, performing any pre-processing calculations, and training machine learning models. This end-to-end project is called an impulse. You can then test your impulse on live data with a connected sensor, and the studio will guide you through the process of creating a pre-compiled firmware or library that will run your impulse on any number of platforms. This includes your pre-processing code, your trained neural network, and any anomaly detection code that you may have so you can perform inference locally without an internet connection or on the edge. In our discussion today, we'll be going over what exactly is Edge Impulse, what is advanced anomaly detection and how is it used, and some various use cases that we see in industrial settings today. Then we'll also be going over a live demo of the Edge Impulse Studio. So, what is Edge Impulse? Edge Impulse is the world's leading embedded machine learning platform. From collecting and labeling your training and testing data, designing and training your machine learning model, testing and validating your model's real life performance, and finally deploying your model to your edge device, this entire process can be done in the Edge Impulse Studio. ML powered solutions from data will drive new value across all industries, from industrial settings like predictive maintenance and asset tracking to quality assurance on factory lines, and human interfaces like occupancy detection, speech recognition, and even predictive healthcare. All of these use cases are driven by the power of the data that we find at the edge. Edge machine learning can empower almost any use case. Depending on your hardware constraints, if you have an ultra low power device, you can do things like anomaly detection or sensor classification, all the way up to a GPU where you can do things like video classification for object detection and image classification directly on the edge. Edge Impulse is enabling all enterprises and developers to quickly create these solutions and deploy them rapidly to the edge. We have over 40,000 developers, 65,000 projects already created with data in the Edge Impulse Studio, and over 100 plus enterprises using our Edge Impulse Studio platform. And we're also trusted by leading enterprises such as Aura, Advantech, Poly, Sony, and Texas Instruments. Today, we'll be specifically talking about enabling continuous learning for edge machine learning projects. Continuous learning for edge machine learning projects particularly pertains to enabling our edge machine learning models to continuously improve over time by sending our anomaly detection data to the cloud and retraining our model and then redeploying that model to our edge device so we can more rapidly detect when our industrial machines are about to fail, for example. We have advanced ML ops infrastructure available for you to protect your data, protect your models, and protect the users that are accessing your data. We have SSO for all of your enterprise accounts. You could store, view, and manage all of your enterprise's data, projects, and users. And you can even connect your own data buckets using platforms like Google Cloud and AWS to directly pull your existing cloud data into the Edge Impulse tool without giving Edge Impulse full access to your data. You can build advanced curable datasets with easy quality control, and you can save time and cost by leveraging Edge Impulse's public cloud integrations. And you can use upload portals to allow your existing third-party customers to upload data securely to your Edge Impulse project. So now that we've discussed what Edge Impulse is, what exactly is advanced anomaly detection? Advanced anomaly detection is when we use machine learning on the edge to identify machine failures before they occur. This is really important because when we have expensive factory machines like robots or scientific equipment, these machines are very expensive and very delicate and difficult to repair. And repairs can sometimes be impossible altogether. However, because there's a bunch of tiny parts in these machines, we can usually analyze the vibration or sound coming from these machines to analyze when a fault is about to occur. So, using anomaly detection models on the edge, we can monitor the health of our equipment before it breaks. And this will benefit quite a few different areas of your factory line, for example, from worker safety, reducing equipment maintenance costs, and reducing overhead. The model essentially works by detecting when data outside of the quote unquote nominal range is detected. And that detection that is outside the nominal range is considered the anomaly. So when your anomaly is detected, we notify our factory operators or machine operators. We can shut down the equipment remotely and then perform maintenance. So now that I know what an advanced anomaly detection model is, how do I make this model? So, depending on your machine and depending on the hardware that you've chosen to deploy your edge model to, and depending on which sensors you've chosen to use for your anomaly detection model, in today's anomaly detection use case, when we go over the live demo in the Edge Impulse Studio, we'll be looking at vibration anomaly detection for an industrial fan or HVAC system. So, using that vibration sensor, I'm going to collect data for two different machine learning classes, one for nominal operation and one for off, when the machine itself is completely off and not running. And this is the great thing about advanced anomaly detection models. We don't need to break the machine in order to simulate when the failure is occurring in order to get that data that looks like an anomaly. We can just record all of the data when the machine is running normally and when it's off. So we don't need to collect data for classes like broken, obstructed, or needs repairs, etc. Once we've collected our data for our two classes for nominal and off, we'll extract the most important features from these classes via digital signal processing or DSP. We'll then train our machine learning model algorithm on the nominal data's most important features. Extracting these most important features from the nominal and off data is really important for making this model as small and as efficient as possible for running on our edge device. And Edge Impulse provides many pre written, freely available DSP blocks for extracting meaningful features from your data directly within the Edge Impulse Studio. And these DSP blocks are essentially just Python's code snippets wrapped in a GUI in the Edge Impulse Web Studio. And there are no black boxes. All the DSP source code is available on the Edge Impulse GitHub. If you have experience writing your own digital signal processing code in Python or MATLAB, for example, you can also write your own custom DSP blocks. And documentation for how you can do this is available on our docs website at docs.edgeimpulse.com. You can deploy your DSP block into a Docker container, host your container directly within the Edge Impulse Studio, or host it on your own platform. You can specify any number of input parameters, and you can completely customize your feature output and labels. We also have a brand new feature within the Edge Impulse Studio called Feature Importance, where you can build advanced anomaly detection algorithms in minutes with the Edge Impulse Feature Importance suggestions, which we'll go over in more detail in the live demo of the studio. In addition to a classical neural network classifier block, we also have a block specifically available for anomaly detection called the K-means anomaly detection block. The K-means anomaly detection block is pre-written and available to use in any sensor data project in the Edge Impulse Studio. You can use your automatically suggested important features from the Feature Importance Explorer and those axes to create your anomaly detection model really easily and quickly. So you'll see here in the screenshot on the right, the features that have been automatically suggested to us as most important from the feature importance tool have been starred in gray. And you can select these suggested axes all in one click within the Edge Impulse tool. Once we finish collecting our data, labeling our data, extracting our data's most important features using DSP, and training our model on these most important features, we can then test and refine our anomaly detection model directly within the Edge Impulse tool without having to deploy anything to the edge yet. So we can use our model testing tab to directly get our classification results from the classifier block or from our anomaly detection block, and we can test without writing any code or deploying to our edge device. We can also calculate how abnormal each frequency band is per sample using the anomaly detection block that we will set up in the Edge Impulse Studio. Once we are ready to deploy our model, we can very easily do that within the Edge Impulse Studio by going to the Deployment tab and selecting from various libraries to directly download and integrate into our embedded firmware application, just as we would any other C++ library, for example. Or we can also build pre-built firmware binaries for various development boards based off of the sensor data that you've uploaded. For example, today we'll be going over a vibration use case. So because I'm using an accelerometer sensor, I can then deploy pre-built firmware that I can directly drag and drop onto our available supported development boards from the Deployment tab in the Edge Impulse Studio. The libraries that you can deploy from the Edge Impulse Studio contain no black boxes. You have full access to the entire source code, including the digital signal processing, the neural network code, and the anomaly detection code, all available for you too. The full source code for the pre-built firmware applications for the various supported development boards is also available for you to use without any black boxes. All the source code is available directly within our Edge Impulse GitHub repository. Just search for the name of the development board and you'll find the associated firmware. So, throughout today's talk, I've been discussing how you can use anomaly detection for a vibration anomaly detection use case for things like HVACs. But I'm just going to go over very quickly a few other use cases to get your creativity juices flowing in terms of how you can use your hardware that you have in your factory or industrial setting, for example, or various devices that you have laying around with various sensor combinations in order to achieve a similar anomaly detection goal. So we have various smart predictive maintenance use cases here. We have air conditioner filter monitoring, sort of similar to the vibration use case that we'll go over in the Edge Impulse Studio demo today. But in this use case, when the filter is slightly obstructed, the device can detect the shape of the high frequency current that's distorted. And we can use our anomaly detection model to alert that on our microcontroller and tell our maintainers that this air filter is clogged. We can also detect circuit breaker aging from things like the vibration pattern during switching. And you can also use the current analysis in our anomaly detection model as well. You can even do things like water or hazardous leak detection through water dropping at several meters with an add-on device or existing hardware can be placed with a vibration sensor near the valves to learn when an open or flush behavior is detected, and we can use that to analyze when leaks are about to occur or are already occurring. We could also do things for motor control and condition monitoring, where we can measure the condition of a motor with multiple sensors using a concept called sensor fusion and analyze all the sensor data coming in at the exact same point to predict when a motor could fail. We can also use anomaly detection for things like ball bearing crack detection with the diagnosis of mechanical faults. And you can also do gas leak detection depending on various sensors that you have for your gas pipelines. So, before we get into the live demo, I'd like to just go over a few further resources that we have available on the Edge of Pulse website so you can get started creating your own anomaly detection model after today's talk. So, we have multiple public projects available for you to directly clone into your own Edge of Pulse account. When you have the access to these slides, just click on the associated project link and you can clone those projects directly into your account, including all of the data, all the DSP code, all the neural network code, all the anomaly detection block information. And you can have that for your own use in your own Edge Impulse account for your own personal devices. We have projects for faucet detection with sound, hard hat detection, banana ripeness detection, smoke detector using TVOC sensors, AC motor fault detection, and fan failure anomaly detection, which is what we'll go over today. We also have a bunch of documentation and tutorials available from the Advanced Anomaly Detection and Feature Importance announcement blog, the Edge Impulse processing blocks documentation, building custom processing blocks tutorials, hosting these custom blocks, and building your own deployment blocks tutorials as well. So now that we know what advanced anomaly detection is and how we can get started, let's go into the live demo of the Edge Impulse Studio. So this is the Edge Impulse project dashboard. For every single Edge Impulse project that you have in the studio, each project is equivalent to one machine learning use case. So the use case that we'll be going over today is fan vibration anomaly detection for industrial devices like HVAC systems and industrial style fans. On the project dashboard, we can see all about our project, who we've shared our project to, the summary of our project, our collaborators, and how we can create our very first impulse or machine learning model from all the way from beginning to end, from acquiring our data, designing an impulse, and deploying our model to our edge device. We can also download all of the intermediate block output exactly as you would with a TensorFlow style development without using the Edge Impulse Studio. So nothing in Edge Impulse is a black box. You have access to all of the intermediate training data and the neural network classifier models and the anomaly detection model as well. Moving on to the devices tab, I can see exactly which devices I have connected to my project. You can easily connect any device that you would like to the Edge Tool Studio and directly collect sensor data from those devices. In this case, I have collected vibration accelerometer data directly from a Silicon Labs Thunderboard Sense 2 into my projects using the Edgeable CLI. You can also collect data over Bluetooth or Web USB directly into your Edgeables project, depending on the board. If you want to send custom sensor data over serial connection to the Edgeables platform, you can also do that as well using the Edge Impulse serial data forwarder. Here we have our data sources tab. This data sources tab allows you to actively pull new data in from whatever pipeline you have connected to your project, whether it be a Google Cloud data bucket or an AWS data bucket. You can connect your data source here, and we have documentation for that in our Edge Impulse documentation. The data acquisition tab is where I can see all of the data that I currently have collected into my project. In this case, I have data for two classes, as we mentioned previously, data for our nominal, data for our fan running at a nominal level, and data for when our fan is off and when the accelerometer is placed different positions around the fan. So this is our training data, and I can click on each individual sample and see what that accelerometer XYZ data looks like on the right. I can also record new data here when I have a device plugged into my project over Web USB or serial data forwarder, for example. I can select the test data tab and see all of the test data that I've uploaded. Because this is an anomaly detection project, I actually have four classes in my test data tab. I have classes for off data, obstruction data, shaking data, and nominal data. And the obstruction and shaking classes is what I'm going to use to prove to you that our anomaly detection model will work in real life on our edge device. For most industrial use cases, you won't necessarily have this shaking and obstruction data, but for today's purposes, we have this here so we can see our anomaly detection model running as it should. Our Data Explorer tab allows us to look at all of our data in a graphical format. And this is a really easy way to see if we have any data that is possibly mislabeled. For example, here is a sample that is labeled as off, but it actually looks more similar to nominal data. So this might be a sample that is mislabeled, and we might need to change it to nominal in order to make sure that our model is trained as well as it can. Because your model is only as good as the training data that you put into it. And if it's anything is mislabeled, you're going to get a not as accurate model on the output. You can also export your data by going back to the data acquisition tab and clicking on the export data tab. You can download all the original files with their uploader compatible names or original file names, and you can export them here and you just get a zip file to download. So nothing in Edge Impulse is a black box. You have access to your data all the way from beginning to end in every single one of your versions of your project. Now let's move on to designing and training our machine learning model. Now that we have our nominal and off classes and our training data and our testing data uploaded, we can move on to extracting our most important features, designing our impulse, and training our anomaly detection model. So the impulse design tab, this is a graphical overview of what the complete ML pipeline looks like. When extracting the most important features using a spectral analysis DSP block, training our classification block or our anomaly detection block, and getting our output features, which is nominal or off in this case. So we save our impulse and move on to the spectral features tab. From this tab, we can see exactly what the raw features of our data look like and the DSP filtered results. In this case, because we're using a spectral analysis block, we're just seeing the things like scale axes, the FFT length, number of peaks and the thresholds, and power edges, for example. And we can see what the signal will look like when it's raw and after the filter. Again, all of these parameters are just various inputs into a Python snippet that we have directly available for you to use for free in the Edge Impulse Studio. Again, all of these parameters and output graphs can be changed if you want to design and write your own DSP custom block. So we're going to then generate our features, and this extracts the most important features from our nominal and off machine learning classes. So we're going to generate these features. Great. Our job has completed. I can see the feature explorer here on the right and the feature importance below on the bottom. This feature importance element is really important for advanced anomaly detection because this allows us to take the guesswork out of seeing which features are going to be the most important for our specific use case. In this case, for fan vibration detection and anomaly detection, we're going to be looking at specifically the accelerometer x axis of the root mean square, the accelerometer y-axis and the root mean squared, and the accelerometer z peak one height. And these peak one height labels are what you can use to. These peak one height labels are labels that Edge Impulse has inputted into the spectral analysis block that we've written and available in the Edge Impulse Studio. Again, these labels of these features can be changed to whatever custom label that you'd like in your own DSP block. But you can also see the source code of this DSP block and why this is specifically called peak one height in the Edge Impulse Studio spectral analysis digital signal processing source code in the Edge Impulse GitHub. Moving on to our neural network classifier. Our neural network classifier is not going to be as interesting in today's example because the anomaly detection is what we're primarily looking at. But this neural network classifier we can train just using a couple dense layers in our input here and 30 training cycles. But this is essentially going to be just a binary classifier to say, based on the incoming accelerometer data, is what I'm seeing nominal or off? We won't get any anomaly detection score information until after we've trained our anomaly detection block. But again, this neural network block is basically just a web GUI that is wrapping over Python code. And you can see exactly what the Python code looks like by clicking on this button here and switching into expert Keras mode. And this is the Python code that you would write exactly as you would if you were training a TensorFlow model on your own computer locally. I'm going to switch back into simple mode here. And now that my model has been trained, I can see that I have 93% accuracy based off only the 3.5 minutes of training data that I've uploaded to my Edge Impulse project. And again, this is basically just a binary classifier. Is my data nominal or is it off? So this is not going to be the most useful information for this specific use case, but I can click on all my individual samples here and see exactly where this window came from on each of my input training data samples. So some of these were mislabeled according to our trained neural network classifier, and you can see those in red. We can also see our on-device performance. In this case, we're estimating for a MacBook Pro, but you can change the estimations on the dashboard, scroll down, and under latency calculations, you can select things like a Silicon Labs Thunderboard, for example. So I'm changing to the Silicon Labs EFR32MG24. I'm going to go back to the neural network classifier block and scroll down, and I can see that the on-device performance has been changed and the latency calculations have been updated to reflect how this model would perform on a Silicon Labs Thunderboard. And we have about 1 millisecond for inferencing time, 1.7K of RAM, and 20K of flash usage. Moving on to the anomaly detection block, this is where I can select the automatically suggested axes from our feature importance feature here. So we can see the features that are super important for this specific use case. And again, these gray stars will change based on your uploaded data, your uploaded training data, and the DSP block that you've chosen. So I'm going to automatically select my suggested axes here, and then I'm going to click Start Training. Once the anomaly detection block has been finished training, we'll get an anomaly explorer where we can see exactly what our testing data looks like compared to our training data and see exactly which samples are going to be considered an anomaly. So here you'll have to scroll around a little bit and zoom in and out, but I selected an obstruction test data sample to compare against my training data over here. And I can change my selected most important axes and my most important feature. So I selected for my x-axis the accelerometer x-axis root mean squared and my accelerometer z peak one height for my y-axis. And this is what gets me this visualization here with my training data. Again, this is my nominal and off normal data of my device running normally. And this is test data where I have an obstruction that's being recorded and obviously anomaly because it's not anywhere near these blue circles on the left. And this anomaly score in the average axis distance, this is what is going to be used to calculate when you get the output in the Edge Impulse SDK when you integrate it into your embedded firmware application. So great, we have successfully trained our neural network classifier and anomaly detection model for our fan vibration anomaly detection use case. Moving on, we can select the Eon Tuner tab, and this is a feature for auto machine learning that is available for free within the Edge Impulse Studio. You can start the Eon Tuner to effortlessly find the most optimal architecture for your embedded machine learning application. We've just skimmed over the neural network classifier architecture today because it's not as important because we're focusing on the anomaly detection block. But the Eon Tuner can create almost an infinite amount of combinations of various layers and features and architectures that you can select from the Edge Impulse Studio to find the most optimal memory usage, latency calculation, and DSP block for your use case and for your selected target. So, for example, this is looking at continuous motion for a Cortex M4F with a 100 millisecond time for inference and maximum 128 target RAM and 1024 kilobyte target ROM. So, this Eon Tuner creates a matrix of all the possibilities that you could have for various neural network classifier blocks. But again, this is more useful for other types of continuous motion classification and not necessarily for anomaly detection. Because we're really just looking at whether the incoming accelerometer data is nominal or if it's off. So moving on, the retrain model tab is what we're going to primarily use for our continuous based learning. I know we've only mentioned it a couple times in this talk, but retraining model is very important. So if we take new data over the cloud and upload it to our bucket, our AWS bucket or Google Cloud bucket, for example, we can use this retrain model tab to automatically detect when new data has been uploaded, and we can retrain based on all our existing known parameters and redeploy with this new information to further refine our model and make our anomaly detection even more accurate. All of these tabs are completely API driven. We have a REST API and documentation for that is available on our docs website at docs.edgeimpulse.com/reference, which you can see here. We have documentation for our ingestion service API, our remote management protocol, our C+ inferencing SDK, and the Edge Impulse API, which is what you can use to create basically a headless version of the Edge Impulse Studio, where you don't need to log into the web GUI. You can do everything automated in a Docker container, for example. So we can just click train model and it both extracts our most important features using the special features digital signal processing block. It retrains our neural network classifier and retrains our anomaly detection block. The live classification tab allows you to directly input a test sample into our trained model. So I'm going to load an obstruction sample into here, and this is exactly how we can test our model before we deploy it to our edge device. So as we've seen here, I've taken my test sample, which was an obstruction, which is obviously an anomaly, which we know is a human, but our model has successfully identified this sample as fully an anomaly sample based on the anomaly score that we see here. And we can see where the sample lies in our anomaly explorer as well. Moving on to our model testing tab, say we have hundreds or thousands of anomaly detections test samples uploaded to our test data set. We can go to the model testing tab and bulk classify all of our samples so we can get the percentage of accuracy that our model will perform in real world. And we can use this tab to determine if we need to add more training or testing data set to our anomaly or off classes, or just add more samples to our test data set so we can validate our real life world results. Of course, this won't exactly be what we will see on our device in real life due to other extraneous factors, but this could get us a good starting point to tell us if we're ready to deploy to our edge device. We have about an 86.67% accuracy, which is pretty good for our use case, considering I only have 3.5 minutes of uploaded training data. But of course, this accuracy will go up depending on the quality of your data, the accuracy of your labels, etc. Moving on to versioning. Because we're doing continuous learning and we're wanting to continuously refine our model over time, say I want to take this model that I've created for an HVAC system in Houston and I want to move it to a different HVAC system to a factory in Arizona, for example. Those HVAC systems will likely be a little bit different. And I'll need to refine my model to determine when faults are about to occur for that specific machine. But I really like how this model is performing for my machine in Houston. So what I'm going to do is I'm going to version my project at this specific point in time on the versioning page. And this essentially just takes all of the data that I've collected at this point, all of the training data, all the test data, all the intermediate model information, all of the extracted features, all of the neural network block parameters, and the anomaly detection block feature axes, saves that up into basically a zip file. And I can go back to that file at any point in time from this versioning tab. And I can name it with anything I want, and I can see the training accuracy and the test accuracy over time change depending on how I've refined my model and which location where I want to deploy this model at. And finally, it's super easy to deploy your model once you're done testing and validating that it's going to work in real life. You can deploy by clicking on the deployment tab, and we have a bunch of different libraries available for you to deploy to in the Edge Studio. Again, the C++ library is the most common one that you'll deploy to for embedded firmware development, but the C++ library has no black boxes and no external third-party dependencies, and it can be compiled with any modern C++ compiler. You get all of the source code, you get the DSP code, the neural network classifier code, and the anomaly detection block code, all available within the C++ library. And information about how to integrate that C++ library into your embedded firmware is available in our documentation. Today, because we have chosen a Silicon Labs Thunderboard, I'm going to select this pre-built firmware and directly compile it and drag and drop it onto my board. Then I will then use the Edge Impulse CLI to start the embedded firmware application directly on my board and do some anomaly detection directly on the edge. The Eon compiler is also specifically available in the Edge Impulse Studio. The Eon compiler gets the same accuracy, but up to 50% less memory than if you're just going to compile using TensorFlow Lite Micro, for example. So our original model would have been 2.7K of RAM and 33K of flash, but using the Eon compiler, we reduced that down to 1.7K of RAM and 20K of flash, so almost 50% less. I'm just going to click build, and then I'll get my pre-built firmware application available to download and drag and drop onto my Silicon Labs Thunderboard. My pre-built firmware application is available and already ready for me to drag and drop onto my board, and you can see instructions on how to do this in this video on the Edgeable Studio output page. So I'm just going to open it in my downloads folder. Okay, great. Now all I've done is I've flashed the firmware onto my development board. I'm going to open up a terminal application and type Edge Impulse run impulse. And this is using the Edge Impulse CLI, and information about how to install this can be found in our documentation at docs.edgeimpulse.com. So edge-impulse-run impulse and press enter. It's going to connect to my board via the serial port. And now I am running my anomaly detection application and model directly on my Edge device. And we can see here, because I am just having the device lay on its side with no movement, it should show as off or nominal. And then when I shake it, the anomaly score will increase, as we see here. And now we have just successfully flashed our Edge Impulse anomaly detection application onto our Edge device, all within a few minutes. Thank you for joining. I would like to thank IoT Central for hosting this workshop. You can find more workshops and Edge Impulse microsessions at iotcentral.io, where this video will also be available on demand. If you have any questions about Edge Impulse, please post a question on our forum at forum.edgeimpulse.com. We'd love to see what you build. Please show us on our forum at forum.edgeimpulse.com, and please sign up for a free Edge Impulse account at edgeimpulse.com. Thank you.